Welcome. In our digital world, we're constantly interacting with systems, doing a million things behind the scenes, whether you're buying a coffee or you're on a massive financial network. But have you ever stopped to wonder how these super complex systems make sure our data stays reliable and nothing gets, lost or messed up? Well, let's pull back the curtain and dive into the world of transactions and distributed databases.
Okay, just think about this for a second. You're booking that dream vacation. Your flight gets confirmed. Awesome. The money leaves your account. But then, the hotel booking fails. You definitely wouldn't want to be stuck with a flight to nowhere, right? This exact problem is what database transactions were invented to solve. The system has to treat the entire booking, the flight and the hotel, as one single all-or-nothing action.
And that brings us to the official definition. A transaction is basically a series of steps that are bundled together as one single unit of work. It is an all-or-nothing deal. Either every single operation succeeds, or the whole thing gets rolled back like it never ever happened. There is absolutely no middle ground.
Now, that idea is pretty straightforward when you're dealing with just one computer, right? But in our hyper-connected world, data almost never lives in just one spot. So what happens when we go from one database to many, scattered all across the globe? This is where things get really challenging.
So on the left, you've got your single database. It's simple. One system is the boss, managing the whole transaction from A to Z. Easy. But on the right, you've got a distributed database. Now, your flight info might be on a server in London, but the hotel data is on a server in Tokyo. Suddenly, you've got multiple, separate systems that have to coordinate with absolute perfection to make sure that all-or-nothing rule is followed.
This diagram here gives us a peek at how that coordination actually works. In the middle, you see the Transaction Coordinator, or TC. Think of it as the project manager. It takes your big request, like book my trip, and chops it up into smaller tasks. Then it sends those little jobs out to the transaction managers, the TMs, at all the different locations. The coordinator's main job is to sit back and wait until every single manager gives it a thumbs up before calling the whole thing a success.
So how on earth do we guarantee this all works reliably in such a complicated setup? Well, engineers came up with a brilliant set of 4, let's call them unbreakable rules that every single transaction has to play by. These rules are the absolute bedrock of modern data processing.
And these 4 properties have a really memorable acronym, ACID. It stands for atomicity, consistency, isolation, and durability. Let's break down what each of those really means.
First up is A for atomicity. And we've actually already talked about this one. It's that classic all-or-nothing principle. A transaction is like an indivisible atom of work. It either completes 100% and commits its changes, or if anything at all goes wrong, it aborts and every single change is completely erased.
So here's what that looks like in practice. The transaction kicks off, it does its thing, booking the flight, then booking the hotel. Then at the very end, there's a huge decision point. Did everything work? If the answer is yes, we commit, and all those changes become permanent. But if anything failed along the way, we abort, and the database is instantly snapped back to the way it was before we even started.
Next up, C stands for consistency. This rule means the transaction has to leave the database in a valid, logical state. Think about it like this. If you transfer $100 from your checking account to your savings account, the total amount of money you have is still the same, right? The transaction can't just invent money or make it disappear. It has to keep the data's integrity intact.
Then we get to I for isolation. In any busy system, you could have thousands of transactions happening at the very same time. Isolation makes sure that all these simultaneous transactions don't trip over each other. It's like each transaction gets its own private bubble to work in, completely unaware of any others happening around it.
This gives you an idea of the kind of chaos that happens without isolation. Imagine 2 people trying to book the last seat on a flight at the exact same moment. Transaction 1 reads 1 seat left. At the same time, transaction 2 reads 1 seat left. They both think they can sell it. Whichever one saves its result last completely overwrites the other's work. It's a total mess, and it leads to corrupt, incorrect data.
But here's the solution. With isolation, this system creates a nice, orderly line. It basically tells transaction 2, hey, hang on a second, T1 is using that right now, you have to wait your turn. So T1 gets a lock, does its work, and finishes. Only then is T2 allowed to go. The end result is predictable, orderly, and most importantly, correct. Isolation prevents these kinds of data collisions and keeps everything consistent. And finally, we have D for durability. This one is the system's rock-solid promise to you. Once a transaction is committed, once the system says, okay, we're done, those changes are permanent, period. They'll survive a power outage, a server crash, you name it.
That data is safely stored away and will be there when the system comes back to life. So now we get the ACID rules, but how do we actually, build these transactions? It turns out there are different strategies, different models for how to organize all these operations, especially in a distributed world. Let's look at two of the most common ways to do it. On the left here, we've got a flat transaction. You can think of this as just a single straight line of tasks from start to finish. It's one self-contained unit. But on the right, we have a nested transaction. This is more like a family tree. A main transaction can kick off multiple sub-transactions, and those can even run at the same time, in parallel.
So the big difference here is really about structure. Flat transactions are simple, sequential, and really easy to manage. But nested transactions? Ooh, they bring some serious power to the table. They let you run smaller tasks at the same time, which is a massive boost for speed and performance. Plus, if one of those little sub-transactions fails, you might be able to just retry it without having to scrap the entire operation. That makes the whole system a lot more resilient.
I know. At this point, this all might seem super technical, maybe a little abstract. But the truth is, these concepts are the invisible engine that powers countless things you use every single day. So let's bring this all back from theory to the real world.
So where's all this happening? Literally everywhere. Every time you book a flight, every time you transfer money online, every time you place an order from an online store, even something as simple as saving a file to Google Drive, or when your phone syncs its data in the background, that's all distributed transactions working hard to make sure everything happens reliably across who knows how many different servers.
And that brings us right back to where we started. The ACID properties, these different transaction models we've talked about, they're what make our modern digital lives possible. They're the guarantee that when you book that flight and hotel, your whole trip is confirmed without a hitch. Or if something goes wrong, the whole thing is safely canceled, leaving you and your money right back where you started.
So the next time you use an app, just take a second to appreciate the incredible, invisible ballet of coordination happening behind the screen. And it leaves us with one big question to think about. In a world that demands instant results, how do we balance the perfect ironclad data consistency of ACID with our nonstop need for more and more speed? Well, that's the central challenge for the next generation of databases. And that's the explanation for today. Thanks for joining me.